Hi, welcome to the second lecture of Math-S401 Dynamic Optimization. Today we're going to see some mathematics that you will use later on in the course. So in particular we will see the concept of a Banach space, and towards this end we're going to first see the concept of a vector space. Then we're going to see a norm on this vector space. I'm going to introduce what a norm is and how to use it. And then we're going to see which kind of properties of this norm, and in particular on converging sequences that you need in order to define a Banach space. And we're going to introduce one particular Banach space that's going to be very relevant for the rest of this course. Okay, so let's start by going to the whiteboard. So first of all, let me introduce the notion of a vector space. So a vector space is a set of objects called vectors. So let me call this X. And in addition to X, it has two operators on these objects. So the first is addition. And the second one is multiplication. And there's a particular multiplication, namely called scalar multiplication. So how are these two things used? Well, a space is a vector space if it's closed under addition and scalar multiplication in the following sense. So if I take two elements in this vector space, then I can form the sum of these two things. I can take the vector x and y. I can make a new vector out of this. It's going to be the vector x plus y. Okay, then this will also be an element x. So this is the first rule of making new vectors out of old ones. And then there's a second rule. If I take a vector x, a vector in big X, and if I take a number alpha, which is a real number, then I can make the vector alpha times x, and this is called the scalar product. And this will also again be a vector. Okay, so any two vectors that I take and can take the sum, and it will give me a new vector. If I have a vector and a number, then the number times this vector will also be a vector and also be a part of x. Okay, so x is closed under addition and is closed under scalar multiplication. And the vector space satisfies some properties, so I'm going to list them here, and most of these properties will be very natural and intuitive. So first of all, if I take two vectors x and y, and I make the vector x plus y, then this is the same as the vector y plus x, right? So this is called commutativity, so we kind of exchange the two vectors under the plus sign. Also, if I take the vector x plus y and I make a new vector by adding z, then this should be the same as adding y and z together and then adding x to this vector, right? So this is called associativity. I can move the brackets from here to here. Okay, then the third property, if I make a vector x plus y and I take the scalar multiplication with alpha, then this is the same as multiplying x with alpha, multiplying y with alpha, and taking the sum. Okay, so I can call this property A, you can call this property B, property C. Then property D, I can take the vector x and make the scalar multiplication of alpha plus beta, which is now a number in R, right? So this is the vector addition, this is just addition in R. Okay, so it's a different kind of addition. And this should be the same as the vector alpha x plus the vector beta x. Okay, so this are all very intuitive properties. And then I also have the properties that if I take the multiplication of alpha and beta, so here this again multiplication in R times the vector x, then this is the same as multiplying x by beta and then taking this vector and taking the scalar multiplication with alpha. Okay, so here these two are both scalar multiplications. This is a multiplication in R and this is a scalar multiplication. Okay, so the multiplication notation is the same, but they're a bit different in terms of mathematics. And then I have another one, and as if I take the vector x and I multiply it by the number 1, well, this doesn't change anything, so I still obtain the vector x. Okay, so all these are properties. And then there are two special things that are not properties like this, but special kinds of elements that should be included in the vector space. So first of all, there should exist a special element, let me call this theta, in the vector space, such that for any vector in x, if I add theta to x, well, nothing happens, I just get x. Okay, so this theta is called the neutral element. It's like a zero vector, right? Adding this vector to your vector doesn't change anything with the vector. Okay, and then I have a second kind of property that's for all vectors in x. There exists another vector, let's call it y, such that if I take x and I add y, then I get theta. Okay, so it's like a annihilation of x. Okay, so normally we call this the inverse of x, and normally we write it also as minus x. Okay, why? Because x minus x, this gives you x minus x is theta, so basically x minus x is 0. It's a 0 element. Okay, so this is a vector space. You have a set of elements that satisfies all these properties. So let me give some examples of vector spaces. Okay, so for example, x equal to the real numbers is a vector space. Okay, so if I take two real numbers, then I can simply add them up and get a new number. Okay, and I can multiply any number by a scalar and give me another number. Okay, so this is probably the easiest vector space that you can think of. Here the neutral element will be the number 0. Okay, and if I have x, then the inverse element will be minus x. Okay, now for another example, I can take the vector space that you probably are familiar with, which is Rk. Okay, so these are k-dimensional vectors, and here in this case, if I take a vector, then this is the same as k numbers. Okay, k-dimensional vector space, Euclidean vector space. So if I have two vectors x and y, then x plus y is the same as the vector where I add each element of x with each element of y. Okay, x2 plus y2 and so on, xk plus yk. If I take the vector x and I multiply it by alpha, then this will be the same as alpha times x1. So multiplying every element by alpha. Okay, so I have two vectors, I get a new vector. I have a vector multiplied by alpha, I get a new vector again. Okay, so this is the normal vector space that we get, and this is also where the term vector comes from. But I'm not limited to these two examples. Okay, for example, I can take x to be, or let me write this infinity, to be the sequence, infinite sequence of numbers. Okay, in particular, let x be the set of infinite and bounded sequences. Bounded means that there exists a number that's bigger than any element in the vector or in the sequence, and there exists a number that's smaller than any number in the sequence. Okay, so if I take a vector x and x, then I can write this also as x1, x2, x3, and so on. Okay, so this will never end. It's an infinite sequence. Then I have a y, which could be, for example, number y1, number y2, number y3, and so on. So if I add these two vectors up, what do I get? I get a new sequence, namely x1 plus y1, x2 plus y2, x3 plus y3, and so on. Okay, so I do element-wise addition and I get a new vector. if I multiply x by some number alpha, then I can define this to be the infinite sequence where the first one is multiplied by alpha, the second one is multiplied by alpha, the third one is multiplied by alpha, and so on. And if these two are bounded, then this one is also bounded, and if this one is bounded, then this one is also bounded. Okay, so adding two bounded vectors, infinite sequences, gives you a bounded infinite sequence, and so on. Okay, so this is also going to be a vector space. So this is an infinite sequence. I can even generalize this more broader. For example, I can take x to be the set of all functions f that goes from some set a, let's say, to r, all real valued functions on a. Okay, so let me take one function f and let me take one function g, and I have to use these two functions in order to find a new function. So for example, let me make the simple assumption that a is for example the real line. Then I have a function f, I have a function g. Okay, I would like to add these two functions together. So how can I do this? Well, I can define a new function f plus g. Let me call this h. And how do I define h? Well, I can say that h of x is equal to f of x plus g of x. Okay, how do I add two functions together? Well, I look at this value, I look at this value, and I add this value to this value, and I get a new value. Okay, so it's element-wise addition of functions. So for example, this will be g plus f. It's not very accurate, but I hope you get the idea. Okay, so for example, if f is equal to, if a is r, right, so I have real valued functions from r to r, then f could be, f of x could be 2 times x, g of x could be e to the power x, then h of x could be, is equal to 2x plus e to the power x, right? It's just element-wise addition of these two functions. Okay, so this is also a particular important class of functions that we, of a vector space that we will use. So I forgot, so here was the neutral element was 0. Here for Rk the neutral element will be equal to the vector of all zeros. Okay, that's easy. Here the neutral element theta would be the infinite sequence of all zeros. Okay, and here, if you think about it, what could be the neutral element here? Theta, well, it could be, it's a function, right? It's an element of x. So here theta of x will be equal to 0 for all x and a. Okay, so it's the 0 function. So there are also some spaces that you could think are vector spaces, but in fact are not. So let me give you some examples. For example, z, the set of all integers, this is not a vector space. So why is this not a vector space? Well, for example, the number 2 is in z, but then if I take a scalar multiplication of 2, for example, 1 over 4 times 2, well, this will not be in z. Okay, so it's not closed under scalar multiplication. So it's not an element of, so this is not a vector space. Another example, I can take the set of all pairs x1, x2, such that x1 plus x2 is equal to 10. Okay, so this is also under normal addition, this is not a vector space. Okay, for example, I can take 5, 5, this will be in this set, right? I can take 1, 9, this will be in set, but if I take the addition of these two, this will no longer be in the set. All right, so not all sets are vector spaces. So the more important things are that's closed under addition and scalar multiplication. Another example in terms of functions, I can look, for example, to all functions f from, let's say, 0, 1 to r plus. Okay, is this a vector space? Well, no, right? So for example, in this is the function that fx is equal to 1 for all x between 0 and 1. But you see that this function under normal addition doesn't have an inverse, right? So one of the properties that we required is that for all x there should be a y such that adding it up should give you the 0. So here I need another function that adding it to f will give me 0, but this is impossible because it has to go to r plus, right? So here minus f of x should be minus 1. Alright, so this is the inverse of f, so this should also be an x, but this cannot be an x because it maps to minus 1, and here it only maps to r plus. Okay, so it's convenient to write down some examples and see whether it's a vector space or it's not a vector space. Okay, so some vector spaces that we will use often, for example, I call it by BA. So this is a set of all functions f from a to r if is bounded. Okay, so what does it mean for f to be bounded? Well, it means that there exists a number in r such that for all x in a, the absolute value of f of x, right? F of x is a number, absolute value is lower or equal to m. Okay, so there's a number that's bigger than any value of f, and there's also a number that's smaller than every value of f. Okay, so this is the set of all bounded functions on A. So this is a vector space. You can show that it satisfies all properties under normal element-wise addition and scalar multiplication. Okay, I haven't defined scalar multiplication here, but it's basically the same. If I have a function and I multiply it by alpha, then I define this to be a new function h, such that h of x is equal to alpha f of x. Okay, I just multiply element-wise. Okay, so I'm jumping a bit back and forward here. So this is an important class, and then another class is c of a that's equal to f a to r as f is continuous. Okay. This is also a vector space. How can you see this? Well, if you have two continuous functions, and if you add them up, then you also again have a continuous function. Okay, so the class of all continuous functions is a vector space. Okay, so let's now go to the next concept, and that's the concept of a norm. So what's a norm? In order to define a norm, first I need to start from a vector space. Okay, so let's take a vector space X, and then a norm is a function, right? And we're writing it like this, with two lines, and then we'll put the element inside, and then we have two other lines. So it's a function, it takes a vector and produces a non-negative number, okay? And it satisfies three properties. So first of all, for all vectors in X, the norm of x has to be greater or equal to 0, right? It maps to r plus, so that's a given. And the norm is equal to 0 if and only if x is equal to the 0 vector, right? The only case where the norm of x is 0 is when x is the 0 vector. Okay, so that's another condition to saying this. Okay, the second one. So if I have a vector x and I take the norm of alpha times x, then this should be equal to the norm of x multiplied by the absolute value of alpha. Okay, so you can take the scalar outside of the norm, but I have to take the absolute value. right? That's the second property. And then the third property, if I take the norm of x plus y, then this should always be less than the norm of x plus the norm of y. Okay, so these are ABC, these are the three properties of norm. Any function that satisfies these three properties on a vector space is called a norm of this vector space. Okay, and so what's the intuition of a norm? Well, if I had two vectors x and y, then the norm of x minus y measures the distance between x and y. Okay, so basically it's a function. This function, the norm, is used to measure the distance between two vectors. Okay. So if I have a norm and a vector space, then x together with the norm is a normed vector space. Okay, and in general you have many norms. So let me give a few examples of norms. So for example, if x is equal to r, okay, so this was our first example, then for an example of a norm. So x is here a number, so for example it could be the absolute value of x. Okay, so the first property, the absolute value of a number will be 0 if and only if the number is 0. Okay, so that's satisfied. What happens if I multiply a number and take the absolute value? Well, the absolute value of a product is equal to the product of the absolute values. So that's the second property. And then for the third property, well, you know that the norm of x plus y is always less than the norm of x plus the absolute value of x plus y is always less than the absolute value of x plus the absolute value of y. Okay, so also this property is satisfied. Okay, then if x is equal to rk, well, a well-known norm is called the Euclidean norm, and the Euclidean norm is, how do I get it? Well, this is a vector of numbers. Okay, so I take the sum of all the numbers squared, and then I take the square root. Okay, so this is called the Euclidean norm. And the Euclidean norm is, I think, the most well-known norm on k-dimensional Euclidean space. So it satisfies all the properties. Well, if this is equal to 0, it means that because here you take the squares, all these elements have to be equal to 0. So you get a 0 vector. That's the first property. For the second one, if I multiply this vector by number, then here I multiply everything by this number. I can take this number squared outside, summation over the same element, and then take the square root, so I have the absolute value of this number outside of the square root. And for the third one, this is a consequence of the Cauchy-Schwarz inequality that we have seen for Math-S401, if you don't remember it anymore. Okay. Then, for example, for x equal to r infinity, right? So all bounded infinite sequences. There are many norms. One norm could be, for example, the supremum of the sequence. Okay, so x will be an infinite set of numbers. It's bounded from above and below, so it has a supremum. Okay, so I should say it like this. It has a supremum and an infimum. So the sequence of absolute values has a supremum, so I take this to be the supremum. Okay, so if the supremum is 0, it means that every element is 0, so I have this 0 sequence. If I multiply everything by a number, I can take outside the supremum with the absolute value. And then the inequality follows because if I have two infinite sequences, well, then by definition this will be the supremum. So I runs over n, right? Infinite sequences of xi plus yi. I know that this is less or equal to the supremum yn n of xi plus absolute value of yi, right? Because of this here. and the supremum of a sum is less or equal to the sum of the supremums xi plus the supremum yi, and this is equal to the norm of x plus the norm of y. Okay, so this is one possible value of the norm. There exist others. For example, I can take x to be equal to the sum y and n of delta to the power I of xi, and here delta could be a number between 0 and 1 not included. It should also not include 0, sorry, strictly between 0 and 1. You can try and you can show that this also satisfies all the properties of a norm. Okay, so here this also only looks at the biggest absolute value. This takes a weighted sum of all the values. And because the sequence is bounded, then this sum will also converge, right? So this is a well-defined norm. So in general, on the vector space, you can have different norms. Okay, there's not a single norm here. So let's go to this set of bounded functions on a set A. Right, so remember these are the set of all functions from A to R, such that f is bounded. Okay, so a particular norm that we're going to be interested in is given by the supremum norm. So it's very similar to this here, but now we take the supremum over all x and a of the absolute value of f of x. Okay, the supremum will be equal to 0 if and only if this is 0 for every value of x. Okay, so we satisfy the first property. For the second property, if I multiply this by alpha, I can take it outside supremum with the absolute value, right? So it satisfies the second property. And then third property is satisfied very much similar to this reasoning here. Okay, so this here is called the supremum norm, or sometimes called the infinity norm. Okay, there are other norms that are sometimes used. For example, if I have the set of continuous functions on, let's say, the interval 0, 1, right? So this is a set of all functions that map from 0, 1 to R. A norm here could be the integration from 0 to 1 of the absolute value of fx dx. Okay, so for example, if I draw this 0, 1, right, this could be f. So what do? I take first the absolute value. All right, so this becomes positive, this is already positive, and then I take the surface below this curve. Right, so here the arched region, the area of this arched region will be the norm of f. Okay, so this is also a norm. You can check all the properties. Okay, so in particular, if I take two functions and I measure the distance between these two functions, this here will be equal to fx minus gx dx. If I take the subnorm, then f minus g will be equal to sub x between 0 and 1 of fx minus gx distance. Okay, so here this looks at the area between the two functions and integrates it, right, and takes this number as the distance. Here, for every x, I compute the difference between these two functions. Okay, take the sub, and this would now be my distance. Okay, so it measures distance between functions, but it uses different kind of numbers or functions to do this. Okay, so all these are examples of norms. Okay, now I'm going to introduce you another norm, and we're going to use it for function spaces. So let me first define a function phi. This will be a very particular function, so it goes from some domain A to R++. Okay, this means that for all x in A, phi of x is strictly positive. Okay, and this R++ is very important. Then let me define a function. It's going to be a norm, right? So I take a function f from A to R. I'm going to define the phi norm of f to be equal to the supremum of x in A of the absolute value of fx, right? So this is very similar to the subnorm divided by phi of x. And this is well defined. Why? Because phi of x is strictly positive, so this number here is always well defined, right? Because I'm defining something that's non-zero and I'm taking the sub over this. Okay. So let x set of functions f from A to R such that f phi exists. Okay, so this is a well-defined set. I can make this function for every function f from A to R. If it exists, then I include it in the set x. Okay, so what does it mean for this to exist? Basically, it means that this supremum exists, right? So when does this supremum exist? Well, it exists when this thing is bounded. So if there exists some number m in R such that for all x in A, fx phi x is smaller than n. Okay, so we can call this the set of functions f AR that are bounded in this norm. This is bounded in the phi norm. Okay, so this is going to be a very special space, and we're going to call this b phi of A. Okay, this x, we're going to denote it by this. So the subscript phi, because we know the function phi, this is a fixed thing. Okay, so in particular, one particular case is where phi is the when phi of x is equal to 1, right? Then basically we're only looking at all the functions here, so phi is equal to 1, that are bounded. Okay, so here we have the set of bounded functions on A. Okay, so this is a special case of this, where the phi function is equal to the constant function. Similar, we can look at not only the ones that are bounded, but the ones that are bounded and also continuous. We call this c phi of A, right? And in a special case where phi of x is equal to 1, this simply gives the continuous functions of on A. Okay, but normally we'll work with this thing here. So let me give you an example. So why do we use this function? Right, so remember here we are looking at bounded functions on A. So let's take A to be equal to R, right? So we're looking at all bounded functions from R to R. Now let me show that for some functions of phi, we can actually make the set bigger. Okay, so for example, let me take phi of x to be equal to the absolute value of x plus 1. Okay, and we know this is strictly positive. So what does it mean to be bounded in phi norm? Well, it means that f of x over phi of x is smaller than some number m. Okay, and f of x over phi of x is equal to absolute value of f of x divided by x plus 1. Okay, so for example, here f could be some function alpha x plus beta, and this will be satisfied by this definition. Okay, so how can I see this? Well, alpha x plus beta divided by x plus 1 should be smaller or equal to m. So, sorry, it should be the absolute value. So alpha x plus beta divided by x plus 1 is smaller than alpha x plus beta divided by x plus 1, and you can always find a number that's smaller than this, right? We should try to find a number such that this is smaller than m. So let's try this. Alpha x plus beta should be smaller than mx plus 1. So this is alpha x is alpha times absolute value of alpha times absolute value of L minus m absolute value of x plus beta, sorry, minus m should be smaller than 0, so we take m to be bigger than alpha and we take m to be bigger than beta, then this condition is satisfied. Okay, so indeed this function here is bounded in the phi norm. However, it's not bounded on R, right? Because this can go to, if alpha is bigger than 0, this goes to infinity as x goes to infinity, right? So it's not bounded, but it's bounded in the phi norm. Okay, so if phi is a linear function, then all linear functions will normally be bounded in this norm. If phi is a quadratic function, then all quadratic functions will be also bounded. If phi is exponential, then you can include exponential functions to this. All right, so basically the set of functions that will be bounded in the phi norm will be somehow of a mirror image of this phi function. Okay, so this is why we use it in order to generalize the set of functions that we can consider in our vector space. Alright, so I already told you that norms are used to measure distances. So once we can measure distances of vectors, we can also talk about sequences of vectors and convergence of this sequence towards another vector. Okay, so let's X be a vector space. In particular, we have a normed vector space, and now we take a sequence xn in X. Alright, so we have an infinite sequence of vectors. So we say that xn converges to the vector xn x if the following holds. Namely, for all epsilon bigger than 0, there exists a big N in N, such that for all n greater or equal to this big N, the distance between xn and x is smaller than epsilon. Okay, so this is the notion of convergence of a sequence in a vector space. In Math-S401 we already saw convergence of sequences of vectors. So this is entirely the same definition, but now it's more general vector spaces. So basically we can also talk about convergence of sequences of functions. Okay, so for this we have a sequence of functions. Here we take a norm on a function, for example the subnorm of a phi norm, right? Depending on the vector space that you want to talk about, depending on the norm, and then we can talk about convergence of functions towards another function. Okay, once we know the distance between functions, we can talk about these things. Okay, so this is the notion of convergence. Related to this, as you already also have seen in Math-S401, we have the notion of a Cauchy sequence. Okay, so remember it's a small deviation from this definition. It says that xn and x, right, so it's a sequence of vectors, is a Cauchy sequence if for all epsilon bigger than 0 there exists an n big N such that for all n m greater or equal to n, the distance between xn and xm is smaller than epsilon. Okay, so this was the notion of a Cauchy sequence. For every epsilon, I can find a number such that anything that's beyond this number in the sequence is arbitrarily close together. Okay, so this was the notion of a Cauchy sequence. So in Math-S401, we have seen when X is a vector space, in particular it's Rk, and this is the Euclidean norm, okay, then every Cauchy sequence was convergent and every convergent sequence was Cauchy. Okay, so on the one hand we have convergence, and on the other one we have Cauchy. And you have seen that in Rk, these two things are the same. Cauchy sequence converges, convergent sequences are Cauchy. So the fact that convergent sequences are Cauchy is true. It's true in general. However, the reverse, that every Cauchy sequence is convergent, when we talk about general vector spaces, this is no longer true. All right. So let me give an example towards this end. Let X be the following vector space. Right. We have a set of all functions 0, 1 to R, and they're continuous. Okay, and you can show that this is a vector space. Okay, adding two continuous functions together gives you a continuous function. The zero element is a zero function. The inverse is just the same function negated. And let me take the following norm on this vector space. It's equal to the integral from 0, 1 of fx dx. Okay, so if we have 0, 1, so we have the interval 0, 1, we have a continuous function on this interval. For example, this one, this is my f. So what's the norm? Well, it's just the area under this curve. Okay, and you can show that it satisfies all the properties of this norm. So now let me construct a sequence of functions. Okay, so what I'm going to do, first I'm going to construct my function f1. So this is 0, 1, 0, 1. Okay, so f1 is going to be the linear function from 0 to 1. Okay, so this is going to be my f1. f2 is going to be equal to 0 up to the point 1/2, and then it's going to go linearly from 0 to 1. So this is my f2. f3 is going to be 0 from 0 to 2/3, right? It's going to be 0, and then it's going to linearly increase to 1. And f4 is going to go to 3/4, and then it's going to linearly increase. So in general, fn is 0 from 0 to 1 minus 1/n, and then linearly interpolate between 0 and 1. I'm not going to explicitly write down this function here, this part, but you can see it's okay. It's a linear interpolation between 1 and 0 in this part here. Okay, so I hope you understand how these sequence of functions work. And you can see every one of these is continuous. Okay, there's no jump somewhere in the function. So we have a sequence f1, f2, and so on, fn, and so on. Okay, so you would like to see what happens with this sequence. So first of all, let me show that it's a Cauchy sequence. Okay, so let me see what happens with fn minus fm, fn minus fm, if this goes to 0, if n and m goes to infinity. Okay, so for fn, I go to 1 minus 1 over n, and then I linearly interpolate. And for fm, I go to 1 minus 1 over m. If m is bigger than n, then this would be to the right, and then I linearly interpolate. Okay, and then I'm using the definition here. Well, it's the integral from 0 to 1 of fnx minus fm x dx. So this corresponds to this area here, right, between these two functions. So if I compute this, is this triangle, which is 1 over 2m, minus the first, this bigger triangle, right, which is 1 over 2n, minus the smaller triangle here, which is 1 over 2m. Okay, so here it's easy to compute 1 over 2n minus 1 over 2m, and you can see when n and m go to infinity, then this goes to 1, this goes to 1, 1 minus 1, this goes to 0. So in other words, this sequence here is Cauchy. The functions get arbitrarily close together. Okay. Now what's the limit of the sequence? Well, you can see if n goes to infinity, this point here where you start interpolating is going to get arbitrarily close to 1. And in the limit, you're going to have a function that kind of looks like this, right? So it will be 0 between 0 and 1. And then at the point 1, it will jump to this point here. Okay, so this is going to be the limit of fn in n. However, you see that because of this jump here, is not continuous. Okay, so this function is the limit of the sequence, but it's not continuous. So if it's not continuous, it cannot be an x, right? Because f was the set of continuous functions here. So here we have constructed a Cauchy sequence that converges to something, but the something is not an x. Okay, so this shows that not every Cauchy sequence converges. So we have seen that from Cauchy to convergence, this is not true. Okay, not always. Okay, so you have to be careful. In this kind of settings, Cauchy sequences do not always converge. Or in other words, Cauchy sequences might converge to something that's not in the vector space. And if it's not in the vector space, well, in our mathematical universe, it's not defined. Okay. So basically what it means in this case that Cauchy sequences do not converge to something in x, it means that x has some kind of non-existing limits, right? There are some sequences that converge to something, but the something is not in x. Okay, so this is an example. For other vector spaces, however, Cauchy sequences do converge to something in a set. Okay, so we say that the set X with the norm vector space, is complete if every Cauchy sequence converges. Okay, so in cases where Cauchy implies convergence, if we have equivalence between these two, then we say that the space is complete. Okay, and now we can define what the Banach space is. Well, we say that X okay, so definition, X with the norm is Banach if it is complete normed vector space. Completely normed vector space, right? So basically it's a normed vector space and every Cauchy sequence converges. This is a Banach space, and we will use Banach spaces in this lecture. So this entire discussion so far has been basically towards the end of defining a Banach space. So what are we going to do? Basically, we're going to demonstrate that C phi A, right? So these are all the functions f from A to R that are continuous and bounded in the phi norm. Is a Banach space, right? So this is going to be our theorem. We're going to prove this after the break. Okay, so welcome back. Recall from previous, so from before the break, that we wanted to prove the following theorem, namely that the set of continuous functions, right, so f is A to R, is continuous and bounded in the phi norm. We wanted to show that this is Banach space, right? And remember, phi was a function from A to R++, and we're going to assume that phi is also continuous. Okay, so it's a continuous function. And we want to show that this set here, the set of all continuous functions bounded in the phi norm, is Banach space. So in particular, every Cauchy sequence in this set should converge to something also in the set. So we're going to do this in two steps. Basically, first we're going to start with the Cauchy sequence. From this Cauchy sequence, we're going to make a candidate function towards this sequence we think will converge. And then we're going to show that indeed the sequence converges to this limiting function, and it's also in the set. Okay, so this is the way we're going to work. So first we're going to make a candidate function for convergence. Okay, so what are we going to do? We're going to take all these functions, right, and we're going to fix them at one particular value in the domain. Okay, so for example, we're going to look at f1 of x, f2 of x, f3 of x, right? So these are different functions, all evaluated at the same point x, fn of x. And we're going to show that this sequence here, this is a sequence of numbers, right? So this is a sequence in R. We're going to show that this converges to something, right? This is going to be the first step. So how do we do this? Well, this is a sequence in R. So in order to show that this converges, it suffices to show that this is a Cauchy sequence, right? Because in R, we know that R is complete. Any sequence in R that's Cauchy also converges. We also only need to show that this is a Cauchy sequence. Okay, so in order to show that this is a Cauchy sequence, we show that fnx minus f of m of x, the distance between these two numbers converges to 0 if n and m go to infinity. Okay, and we know something about the Cauchy. So in particular, we know that fn minus f of m, the phi norm here, goes to 0, right? So we want to make use of this here. So how can we do this? Well, let's pre-multiply this by phi of x, and then fn of x minus fm of x divided by phi of x. Okay, so this is for one particular value of x, which is smaller than the supremum. So this is smaller than phi of x and the supremum over all x of this expression. But then this is equal to this norm here. So fn minus fm of phi. So this term here goes to 0. This is a fixed number. If we keep x fixed, right? This was the deal here. X was fixed. So we know that if n and m go to infinity, this will go to 0, right? So this sequence, the sequence in R, and we know it's Cauchy, and any Cauchy sequence has a limit. So this converges to some number, okay, and we will call this number f of x. Why it becomes immediately obvious? Because we can do this for every x, right? So for any x in the domain, we can make this sequence. We have a Cauchy sequence, it converges to something, we call this f of x. So this defines a function f going from a to r. Okay, basically f is the pointwise limit of this sequence of functions, right? At every point you look at the sequence, it converges to something, we call this limit the function f. Okay, so we want to show that f, first of all we want to show that this sequence indeed converges to f, okay, and second we want to show that it's in the set. Okay, so A, we want to show that fn minus f, okay, so this converges to 0. This means that this sequence converges to f. And B, we want to show that f is in C phi of A. So let's start with A first. So fn minus f, this thing here, remember this is equal to the supremum of x over A of fnx minus f of x divided by phi of x. Okay, so let's first have a look at this term here. Okay, so we have fnx minus f of x divided by phi of x. Now what's f of x? F of x is the limit of this sequence here. Okay, so we can simply substitute this. Here we have fnx minus limit, let me go it for m going to infinity, of fm of x. Right, so we keep x fixed, divided by phi x. So the absolute value is a continuous function, minus is a continuous function, so we can take the limit outside of, we can put it in front of this expression. Alright, so this is limit m of fnx minus fn x divided by phi x. Alright, so this is here is an expression in x. So this expression will be lower than the supremum over all x in A. Okay, so the limit of something that's smaller than something else, the limit of this something else is greater or equal to this limit. Okay, so we know that this is less or equal to the limit of m of, if you take the supremum here, basically we have the phi norm of fn minus fn here. So in the end what we have is we have that fn x minus f of x divided by phi x is less or equal to the limit of m of f, the phi norm of fn minus fn. Now this is an expression in x. On the right hand side we have something that doesn't depend on x anymore, right? There's no x here. This is simply a number. It's a number in R, and this is a limit of a sequence of numbers. So there's no x involved anymore here. So for any x, this will be an upper bound, right? We have taken x arbitrarily. So this is an upper bound of this bunch of numbers in x. So we know it will also be greater or equal to the supremum over all x in A. Okay? And the supremum over all x in A, well, this is equal to this here. So this is equal to fn minus f. The phi norm is less or equal to the limit m of fn minus fm, the phi norm. So now we have this expression. What we can do on the left and the right hand side, we can take the limit of n going to infinity, then we have to take the limit of n and m going to infinity, and we know that this goes to, this doesn't go to, but this is equal to 0. Why is this equal to 0? Well, because of the Cauchy condition. Okay, so this shows that the limit of fn minus f, the phi norm, goes to 0, or equivalently fn minus f phi converges to 0, right? So the sequence fn converges to the sequence f in the phi norm, which is this here a that we wanted to show. Okay, so that's for property A. For property B, if you want to show that it's in the set, well, we have to show two things. It's bounded in the phi norm, and second, we have to show that it's continuous. Okay, so I leave this up to you if you want to try it for yourself. It's not too difficult. Let me show continuity, and then we're done with this quite long proof, I would say. So what do we need to show for continuity? Well, we need to show that if you have a sequence of xn's converging to x, so this is a sequence in A in the domain of the function, right? Then f of xn converges to f of x. Okay, and this is in R. This is a sequence in R. So here convergence is in A, convergence is in R. Okay, so that's the definition of continuity, as you have seen it also in Math-S401. Okay, so because the function phi is continuous, we can equivalently show that if we divide it by x phi n and this divided by phi x, then this should also converge to this, right? So this is equivalent here. It doesn't matter if I divide it by phi of xn, because this function here is continuous. So let me show this here. F xn divided by phi of xn minus f of x divided by phi of x. Okay, and I want to show that this goes to 0. Well, what I'm going to do is I'm going to add and subtract several terms. I'm going to start with the first one here. I'm going to add and subtract several terms and use the triangle inequalities. Right, fxn divided by phi xn. Then I'm going to take this function in this sequence here. Let me call this fm. I'm going to evaluate it at xn. And I'm going to divide it by phi xn. Okay, and of course, because I've subtracted here, I have to add it here. Fm xn divided by xn. Then I'm going to add and subtract another term, which is going to be fm evaluated at x, which is this limiting value here, divided by phi of x, and then the last term f mx phi of x minus f x phi of x, which is going to be the last term. Okay, so you see that I've added subtracted this one, and I've added and subtracted this one. So here phi xn is the same, and here this basically is a phi difference between f and fm. Okay, so this whole thing here is smaller or equal to f minus fm phi, right? Because this here takes the supremum over all x's, and here I have evaluated it at xn. Okay, and the second one here, fm xn phi xn, let me copy paste this. Okay, and the third one here, I can do the same as in the first one. I evaluate it at x. If I evaluate it at the supremum, it's going to be less or equal to fm minus f in the final. Okay. So by taking m big enough, here I've chosen m arbitrarily, so I can take any value of m that I want, right? So taking m big enough, this will go to 0, right? Because fm converges to f. You already have seen this here. This one will also go to 0. So I can take m arbitrarily large so that this becomes arbitrarily small and this becomes arbitrarily small. And now here I have, this will converge to this thing here in the denominator because phi is continuous by assumption. And this will converge to this thing in the numerator because fm is continuous. Okay, so by taking m big enough, I can make these two things arbitrarily small. By taking xn close enough to x, I can make this thing arbitrarily small. Okay, so this means that this, for n going to infinity, can be made arbitrarily small, so this will converge to 0. So this basically is how we show continuity of this limiting function. So this concludes the proof, and it shows that this set of functions C phi of A, right? These are all the continuous functions on A that are bounded in the phi norm. This is a Banach space. And in particular, if we use the function phi to be the constant function, right? So then we have all continuous functions on A that are bounded, not in the phi norm, but in general bounded. But this is a special case of this one here, so this is also Banach. Okay. So this is a special case of this. The proof follows almost identical lines, except that you don't have to care about the phi function popping in here and there. Okay, so this is the end of this lecture. Thank you for watching.